Hello and welcome to the video presentation of our paper titled Underwater Image Super Resolution Using Deep Residual Multipliers. All authors of this paper are from the Interactive Robotics and Vision Lab, University of Minnesota, Twin Cities. The automatic generation of high-resolution images from low-resolution measurements is an active research problem in computer vision and robotics. For visually guided underwater robots in particular, the single image super resolution, in short SISR, allows zooming in interesting image regions for a detailed perception, as shown in this figure. The SISR capability is also useful in tracking fast-moving targets or surveying distant coral reefs. Although a large body of literature offers very good SISR solutions for terrestrial images, those are not directly applicable for underwater imagery due to its domain-specific optical distortion models and due to the presence of a unique set of object categories. A lack of benchmark datasets is another reason why SISR for underwater images has not been explored in depth. Moreover, many state-of-the-art approaches do not adhere to the single-board computational constraints which are important for real-time robotic deployments. We attempt to address these limitations in our paper. First, we propose a deep residual network-based model for 2x, 4x, and 8x SISR of underwater images. We provide a generative and an adversarial training pipeline for the model, which we refer to as SRDRM and SRDRM-GAN, respectively. We also perform thorough experimental evaluation of the proposed models to analyze their utility in real-time applications. In addition, we present a large-scale dataset named USR248, which facilitates supervised pair training of underwater SISR models. We also provide a benchmark evaluation of several state-of-the-art models on its testset and compare the results with our proposed models. We have released this dataset for academic research purposes. Now, let's have a look at the network architecture of our proposed model. The core element of our model is a fully convolutional residual-in-residual model. We denote it as a deep residual multiplier, in short DRM, because it scales the input feature's special dimensions by a factor of 2. It consists of 8 repeated local residual blocks within a 3-layer global residual network, which eventually learns 256 feature maps for the 2x interpolation. This is a modular design, and hence multiple DRMs can be sequentially stacked for higher scaling factors. For instance, 1, 2, or 3 DRMs with additional bottleneck layers can be used in a series for 2x, 4x, or 8x super resolution, respectively. We follow this setup in our implementation. Specifically, SRDRM offers the choice of using 1, 2, or 3 DRMs with the high-resolution output set to 640 by 480. As mentioned, it can be trained as a standalone generative model or alongside an adversarial discriminator. The adversarial model, SRDRM-GAN, uses a 9-layer Markovian patch-GAN-based discriminator, as shown here. Please refer to the paper for the detailed design and parameter specifications of both SRDRM and SRDRM-GAN. We formulate the SISR as an image-to-image translation problem and train both the models on paired data to learn a mapping from low-resolution input images to high-resolution outputs. To supervise the training, we adopt 2 standard loss functions that evaluate the generated images compared to their respective ground truths. As shown, the global similarity loss term is computed on RGB space, and the image content loss term is computed on VGG19 space. In addition, we utilize a perceptual loss term that evaluates part-channel disparity for a smooth SISR learning. A linear combination of these 3 loss terms gives the total loss. Contributions of each loss terms are defined by empirically tuned scaling factors. The combined loss is used as the objective function for generative training, while for adversarial training, we add the traditional GAN loss into the objective. For large-scale supervised training of these models, we collected natural underwater images by numerous oceanic explorations and field trials. We also collected images from a few publicly available online media resources, such as Flickr and YouTube. We made sure that the images capture diverse scenes and contain important objects of interest, such as coral reefs, fish, divers, robots, wrecks or winds, etc., over a variety of backgrounds and water body types. Once the high-resolution images are carefully selected, we use the standard Gaussian blurring and bicubic downsampling techniques to prepare their respective low-resolution pairs. As mentioned, the high-resolution images are set to 640 by 480, and 3 sets of low-resolution images are prepared for 2x, 4x, and 8x SISR training. We also prepared a separate test set with 248 images for benchmark evaluation. We use TensorFlow Keras libraries to implement the training pipelines for SRDRM and SRDRM-GAN on USR248 dataset. We also trained several state-of-the-art generative models named SRCNN, SRResNet, and DSRCNN, and state-of-the-art adversarial models named SRGAN, ESRGAN, and ADSRGAN. Details about their training and implementation can be found in this GitHub repository shown here. We conduct thorough qualitative and quantitative evaluations of these models, which we will present next. At first, we perform a quantitative evaluation based on two standard metrics for image quality analysis, PSNR and SSIM. PSNR stands for peak signal to noise ratio. It measures image reconstruction quality based on mean squared error with respect to the ground truth. On the other hand, SSIM stands for structural similarity measure. It evaluates luminance, contrast, and structural properties of the generated image patches compared to the ground truth. We also conduct performance analysis based on EYQM, which stands for underwater image quality measure. It is a linear combination of three metrics that quantify underwater image colorfulness, sharpness, and contrast. This table summarizes the test set performance of all models in comparison based on PSNR, SSIM, and EYQM. The results indicate that SRDRM and SRDRM-GAN produce comparable scores despite having a considerably shallower network architecture than the state-of-the-art models such as SR-GAN, DSR-CNN, or EDSR-GAN. The proposed models also perform consistently better than other simpler models such as SR-CNN or SR-ResNet. We also notice that the performance for 8x SISR is relatively poor across all models, which validates the inherent difficulty of the SISR problem beyond the 4x scaling factor. Qualitatively, we observed that the generated images for up to 4x SISR are comparable to the ground truth. As shown in this example, the sharpness and texture details are mostly recovered, whereas the contrast is significantly enhanced in the foreground regions. However, such detailed restoration is generally missing for 8x SISR as illustrated in this comparison. Nevertheless, the generated images are still significantly sharper than using traditional bicubic upsampling techniques. We now show a couple of examples of qualitative performance comparison for 4x SISR. In our evaluation, we find that SRDRM performs at least as well and often better than other generative models named SR-ResNet, SR-CNN, and DSR-CNN. On the other hand, although ESR-GAN and EDSR-GAN often fail to restore the sharpness and global contrast, we find that the GAN-based models, particularly SR-GAN and SRDRM-GAN, achieve a better texture recovery than SRDRM and other generative models. We postulate that the patch GAN-based discriminator contributes to this, as it forces the generator to learn high-frequency local texture and style information. A more comprehensive analysis can be found in our paper. The experimental results presented so far suggest that both SRDRM and SRDRM-GAN can provide high-resolution visualizations for low-resolution image patches, which is potentially useful in visual attention modeling and detailed scene understanding by visually guided underwater robots. We also evaluate their computational complexity on embedded robotic platforms to analyze their practical utility. As shown in this table, the memory requirement of SRDRM or SRDRM-GAN is less than 12 megabytes, and it runs at up to 7 frames per second on single-board computers such as NVIDIA Jetson TX2. Therefore, it essentially takes about 150 milliseconds for a robot to take a closer look at a low-resolution image patch. Such computational aspects are admissible in near real-time applications. In summary, we presented a generative and an adversarial model based on deep residual learning for underwater image super-resolution at 2x, 4x, and 8x scales. We also presented a large-scale dataset that facilitates supervised training of underwater SISR models. Our qualitative and quantitative evaluations suggest that the proposed models can learn to restore image qualities at higher spatial resolutions. They also offer fast inference on single-board platforms and hence are suitable for robotic deployments. We conclude by acknowledging the support from our research sponsors. Thank you.